Welcome, my dear students, on a new lecture on functional analysis. So, we have discussed that for any given space, Y is actually a subspace of or subset of Y perpendicular. Now, we have to examine what is the condition that this should becomes equal. So, the natural condition is that if Y is a closed subspace of a Hilbert space, then this should be equal. So we can formally quote that as a result. If Y is a closed subspace of a Hilbert space H, then Y is equal to Y perpendicular. So this is the condition for Y and Y perpendicular to be equal. So let us prove this. So we have already established that Y is a subset of Y perpendicular. We have already established that. Now it is enough to prove that Y perpendicular is a subset of Y. Okay. For that, let X be an element in Y perpendicular, which implies since X is an element of H, because all of them are subspaces of H. Now by theorem 3.3.4, every element can be written as a unique representation of the sum of two other elements. Every Hilbert space H can be written as some Y direct sum Z. So X can be written as X is equal to some Y plus Z, where Y is an element of capital Y and Z is an element of Y perpendicular. Z is an element of Y perpendicular. This we have already proved that. So we have to quote this theorem. Okay. Now moving on, we need to prove that this X is an element of Y. That's what we need. So since we have already established that Y is a subset of Y perpendicular, so Y element of Y implies Y element of Y perpendicular. We have already proved that X is an element of Y perpendicular as well. Now perpendicular space is actually a vector space. So this is a vector space by previous result is a vector space, and X and Y elements of it. Then X minus Y should also be an element of Y perpendicular. Okay. So X minus Y is an element of this implies Z is equal to X minus Y, because we have explained that X is equal to Y plus Z. So Z is an element of Y perpendicular. Thus, we have established that Z is an element of Y perpendicular and Z is an element of Y perpendicular. So Z is an element of Y perpendicular and Z is an element of Y perpendicular. The only element which is common to both of these is actually the identity element. Or, in other words, we can safely say that Z is perpendicular to Z, which means inner product Z is equal to 0, which implies norm Z square is equal to 0, which implies norm Z is equal to 0, which implies Z is equal to 0. That's the idea. Or in other words, we know that Y perpendicular intersection Y perpendicular is set 0. So Z is common to both of them means Z is equal to 0. So Z is equal to 0 means we have written that X is equal to Y plus Z, where Z is equal to 0, which implies X is equal to Y. So where y is an element of y. Since y is equal to x, we can say that x is an element of y. Thus, we have proved that we have started with an element x, which is an element of y perpendicular perpendicular. So, x is an element in y perpendicular perpendicular. We have proved that x is an element of y. That is, since x is arbitrary, y perpendicular perpendicular is a subspace of y. Combining these two, we get y is equal to y perpendicular perpendicular whenever y is a closed subspace.